Okay, so I'm just going to go through the advance notice for the third paper, Unified. I'm just going to go through the oscillations. Okay, so this is the mark scheme from Unified Physics. It's just at the moment I've been all say my tongue, so I'm finding it very hard to speak right now. But okay, so let's go through SHM. So remember the equation for SHM. The acceleration is proportional to the displacement, but but the acceleration is directed towards the equilibrium position. Now, just try to remember that omega equals 2 pi f. I mean, I think this is in the formula booklet, right? So omega equals 2 pi f, and you may be expected to calculate the amplitude or something. So yep, so omega equals 2 pi f, and then the maximum acceleration is where you have maximum displacement. In this case, the maximum displacement is the amplitude. So a equals minus omega squared a, and in terms of the frequency, because you know that omega is 2 pi f, you square all of that and then you substitute into the equation. Part B, maximum energy is transferred between tower and sphere. This is a damping type question. So allow causes maximum damping of the tower or maximum amplitude of the sphere. And part 2 of the same question, when sphere is driven to the natural frequency of the tower in this forced oscillation. So remember, if you are to force a system, so if you were to drive, if you were to, yes, okay, so if you were to force a system to its natural frequency, then it will resonate. And this is when maximum energy is transferred, because then there's maximum amplitude. Now for this question, part C, you know that F equals kx, and you know that A equals minus omega squared x. So, and you also know that F equals ma. So we can equate ma with kx. Just taking the amplitude just for the moment, so ignore the minus for the moment. So because you know that A equals omega squared x, you put m omega squared x equals kx, you equate them together. And then you rearrange for omega, you get omega equal to square root of k over m. Okay, so back to the equation. Omega squared equals k over m. Therefore, you know that omega is 2 pi f. So 4 pi squared f squared equals k over m. Or you can use ka equals ma, because you know f equals kx and you know f equals ma. When x equals a, then you know acceleration is maximum. Right, then just work out k. So you need to be able to rearrange this. And then for part C2, this is the stored energy, right? The stored energy of the spring. Because the stored energy is equals half kx squared, or x equals the amplitude. And so that is where you have the stored energy. So yeah, so let's go back to this one here. So this is stored energy. So the stored energy, half kx squared, is the stored energy in the spring, and the total energy is potential energy plus kinetic energy, isn't it? So I'm just focusing here. And the stored energy is half kx squared, kinetic energy is half mv squared. So in this case, k is the spring constant, x is the displacement, m is the mass of the thing that's oscillating, and v is the speed of the thing that's oscillating. So here, when it's at this end here, the speed should be 0 if x is equal to the amplitude. Here, the speed is when it's maximum. Here is where there shouldn't be any speed because the displacement is now at minus x, where that's the amplitude. So the speed is 0, but the maximum energy is stored in the spring, which is this one right here. Here, again, when it passes through the equilibrium position, that's the maximum speed. So therefore it's half m maximum speed squared. These are the wave experiments. I've copied it from the spec. Okay. Right, so this is one of the experiments for the waves. So this is for finding out the frequency of the wave when you are reflecting a sound wave off a liquid. So this should be open, right? So this should be open. I don't know why I've drawn that there. So that should be open. And this is what you should get, right? And if you were to have a second, let's see, it should be, then, oh, right. So if this is open end, you have a node here. So in this case, if this was L, then the wavelength is 4L, right? Again, if this was L, we need to split that up. So that's 1, 2, 3 sections. So you want 3 over 2L equals lambda. Right, let me just talk about the procedure here. So the procedure: set up the apparatus as shown, fill the tube with water up to approximately 3/4 of its height, take measurements to determine the distance from the top of the tube to the surface of the water, position the speaker above the tube and adjust the frequency until the level of sound increases, indicating resonance. Use the oscilloscope to determine the frequency of the signal. Keeping the signal at the same frequency, reduce the water level until a new resonant point is identified. Take measurements to determine the distance from the top of the tube to the surface of the water. Repeat the experiment to obtain additional readings, continuing to maintain the same frequency. Use this data to determine the wavelength of the sound wave. Using your calculated wavelength and measured frequency, determine the speed of sound in air. Right, this is how you would use an oscilloscope, right? So an oscilloscope, a cathode ray oscilloscope, is a laboratory instrument used to display, measure, and analyze waveforms of electrical circuits. It can therefore be used as an AC or DC voltmeter. An AC voltage on an oscilloscope is represented as a transverse wave, therefore you can measure its frequency, time period, and peak voltage. A DC voltage on an oscilloscope is represented as a horizontal line at the relevant voltage. The x-axis is the time and the y-axis is the voltage or Y gain. Right, let's just quickly do this example. A cathode ray oscilloscope, CRO, is used to display the trace from a sound wave. The time base is set at 7 microseconds per millimeter. What is the frequency of the sound wave? And you're given 2 centimeters on the base and 1 centimeter in the y-axis. So first, how would you do this question? First, you need to use the scale. Secondly, you need to work out the distance of one wave. Then you can work out the period. Then you can convert the length into sound. You can convert the length into a unit of time. Right, so my working out was here. So if you look at the two crosses on the squared grid, that's 3 squares. 3 squares meaning it's 6 centimeters. And you know that 1 millimeter is 7 times 10 to the minus 6 seconds. So you want 60 millimeters. 6 centimeters is 60 millimeters. So therefore 60 millimeters is 60 times 7 times 10 to the minus 6. And you get 420 times 10 to the minus 6. And then because this is the period, you want to work out the frequency. And frequency is 1 over t. And so we end up with 2,380.95 hertz, which rounds up to 2.4 hertz. This is just extra information. Right, so the period of the wave can be determined from the time base. The period of the wave can be determined from the time base. This is how many seconds each division represents, measured commonly in seconds per div or seconds per centimeter. Time base. This control has units of time per centimeter, time per div, and has a range of 100 milliseconds to 1 microseconds per centimeter or division. This is just the harmonics of an open end and a closed end. Similarly here, when you have pieces of a string, these are the harmonics. And here, if both ends are open, these are the harmonics. This is one of the pegs for nuclear and particle physics in the OCR spec. So you are expected from the specification to know the half-life of an isotope, techniques and procedures used to determine the half-life of an isotope. 6 markers. There are previously there are like 2 6 markers in the unified physics. Now this is the usual setup. What equations do you use? What is the procedure and what is the analysis? So let's have a look at some of the mark schemes. So if you look at the mark scheme here for 6 marker, to get the full 6 marks, you need to have clear determination of input energy, procedure, and analysis. Now, when it says input energy, you need to use an equation, right? So, for example, to calculate GPE, you need to use MGH. Use a ruler to measure the length of the tube. Using a top pan balance to measure the mass of the magnet. Record the number of inversions, for example. So for a 6 marker, you need to include some equations that you're thinking of using. What do you need to measure? What instruments do you need to measure? And then the procedure, right? The procedure is number 2. This is about electromagnetism and capacitance. So the procedure will be to invert the torch n times, make sure the magnet falls the full height h between inversions, switch torch on, use stopwatch to 0.1 seconds, so this is the resolution, to measure the time t taken until LED goes out, use a darkened room, measure the final potential difference, measure the final charge stored by the capacitor, repeat experiments for different n. And then you do the analysis. So the analysis would be calculate work done, which is power times time, because in the question I'm guessing they give you the power as 50 milliwatts. Calculate work done equals half CV squared, and then you calculate the efficiency, compare efficiency values, plot a suitable graph. So ideally you want a straight line, so you should rearrange the equation. And then to get a straight line, you need to put the independent variable on the x-axis, put the dependent variable on the y-axis, put the equation in terms of the independent variable, and then whatever the gradient is, that will be the coefficient in the equation. And then it says the last part, discuss the shape of the graph, discuss the gradients of the graph. Okay. This is another 6 marker. So again, the procedure, use the formula n lambda equals d sine theta, n equals 1 because it's the first order spectrum. Find d using the number of lines per millimeter. Find theta using distance of grating from a plastic ruler, not a protractor. And then part 2 is the determination of wavelength. So this is the calculation. So number 1 is the procedure, number 2 is the determination of the wavelength. So this is the actual calculation. Allow use of small angle rule. Okay, so yeah, so part 2 is the calculation, and then part 3 is the estimation of the uncertainty. So this is uncertainty for part 3. So for 6 marker, this one, you need to have a clear procedure, clear determination of wavelength, plus a reasonable estimation of uncertainty. This is another 6 marker. You need to have a clear description, some measurements, and full analysis. So the description would be to to say signal generators, AC supply connected to coil, coil Y connected to voltmeter oscilloscope, use oscilloscope to determine period, adjust signal generator to or use of rheostat to keep current constant, and then the measurements. You vary F, you measure V, you keep the current in the coil constant. How would you measure EMF? For example, height against Y gain on the oscilloscope. Detail on how to measure period on the oscilloscope screen using time base N, hence F. And then the analysis. Determine F from the period. Plot a graph of V against F. Relationship valid if straight line through the origin. So again, these is like a 3-part in the 6 marker. 3-part. This is the 3 sections. Another 6 marker. Clear description and analysis. So description would be to the description would be to describe how you're going to be measuring it, and you need to include the instruments and what you're measuring. And then the analysis, in the analysis you always have to say what graph you're going to plot. Is it going to be a straight line? And then any calculations, any further calculations.